In the last class, we have seen the Taylor series expansion of a function, and it says that if f is a real valued differentiable function, which is differentiable infinitely many times in a neighborhood of x naught, then f of x can be written as f of x naught plus f dash x naught by 1 factorial into x minus x naught plus etc. as an infinite series. So this expansion is called the Taylor series expansion. So the question is, how come this is true, or how to show that f of x can be always represented as a series of this form whenever it is differentiable infinite number of times. So in Taylor's theorem, we show this. Now suppose the Taylor's theorem assumes that the function f from a closed interval ab to r is differentiable n number of times in open interval ab, and fn minus 1 is also continuous in the closed interval ab. Of course, if f is differentiable n times, fn minus 1 will be continuous in the open interval ab, but we have to assume that it is continuous in the closed interval ab also. Now let x naught be a point in the interval a comma b. Then for each x belongs to AB, we can find a C between x and x naught. So we have an x naught and we have fixed x naught, and take any x. Then in between x and x naught, you can find a C such that f of x becomes equal to the Taylor series expansion for the first n minus 1 term plus a last term which contains that function's nth derivative at C divided by n factorial x minus x naught raised to n. It's almost looking like the Taylor series expansion truncated at the nth stage. So we define m such that f of x equal to f of x naught plus f dash x naught by 1 factorial into etc. plus the n minus 1th derivative, plus the last term will be taken as m into x minus x naught raised to n, and such an m always exists. Why? Because f of x is a real number. Once you fix an x, f of x is a real number, so the right side contains many polynomial expressions. So these are all real numbers plus some real number into x minus x naught whole power n. Of course, this m will depend on x. M will be a number depending on x, and you know that one real number can be made to the other real number by adding this type of a term with m value varying. We will fix what is that m. Okay. Now the next step is to define a function such that that function vanishes when f of x is equal to the right side. So what I do is I'll define g of t as f of t minus the right side expression where x is replaced by t. So both sides you replace x by t and define f of g of t is equal to f of t minus this expression. And observe that this g of t is defined for every t belongs to AB, because f of t is defined and this is just a polynomial. So this is always defined for every t. So in particular, this is defined for t belongs to AB also. F is defined only in closed interval AB. The remaining terms are defined for every t in R. Okay. So this g of t is a well defined function. And you also know that g of x is equal to f of x minus the right side with the t replaced by x. So since our m is such that f of x is equal to this will become f of x minus the same. So it will be 0. So g of x is equal to 0. Then g of t is differentiable n times in open interval AB because it is just f of t minus a polynomial. Polynomials are differentiable n number of times, right? Any number of times. And f of t is defined n number of times. So g of t is a differentiable function. And what is g's nth derivative at t? It will be f's nth derivative at t minus m into n factorial. This is because g's first derivative is equal to f dash t minus the derivative of this polynomial. And if you differentiate it n times, what you have to apply is a polynomial of nth degree. If you differentiate n times, it becomes a constant. So if you differentiate a first degree polynomial, this is a constant. So first derivative itself, this will be 0, and for this second term, the second derivative with respect to t will give you 0 because it's a first degree polynomial, etc. This term, it's an nth degree polynomial in t. So when you differentiate g n times with respect to this t, we will have this term vanishing because it's an nth degree n minus 1th degree polynomial. So once you differentiate n times, it will vanish, but the last term will remain, and that will be just m into n into m into the derivative of this will be n into t minus x naught raised to n minus 1, which again if you differentiate you will get n into n minus 1 into n minus 2 into etc into 2 into 1. So that will give you m into n factorial. So g's nth derivative at t is going to be fn t minus m into n factorial. So if you show that g has its nth derivative at some point c vanishing, then the problem is over, because if gn of c equal to 0, you know that fn of c minus m into n factorial is equal to 0. So what will be m? M will be just fn of c divided by n factorial. So that will prove everything, that the existence of m, and m will be obtained as the required one, that is fn c divided by n factorial. Now observe that g of x is equal to 0. As I already told, it's f of x minus the same thing, so it will be 0. Now g of x naught is equal to 0. Why? Because g of x naught is equal to f of x naught minus f of x naught minus all this expression. If you put x naught t equal to x naught, this will vanish if you assume t equal to x naught, then all the terms on the right side will vanish, and this f of x naught will get cancelled with f of x naught, so that will be 0. So g of x naught is equal to 0. Now we can show that g dash x naught is equal to nothing but f dash x naught minus f dash x naught. That is also 0, etc. G's n minus 1th derivative at x naught also will be 0. Now we have two numbers, g of x is equal to 0 and g of x naught is also equal to 0. So g of a equal to g of b means you can apply the Rolle's theorem, right? So here g of x equal to 0 and g of x naught is also equal to 0. So by Rolle's theorem, you can say that there exists an x1 between this x and x naught such that g dash vanishes at x1. So g dash x1 is equal to 0. Now you consider this g dash x naught equal to 0 and g dash x1 also equal to 0. So in between this x naught and x1, you can find again by Rolle's theorem, we can find an x2 between x naught and x1 such that g double dash of x2 equal to 0. Now we consider this g double dash of x2 equal to 0 and g double dash of x naught equal to 0. So in between x naught and x2, you can find a g triple dash x3 equal to 0. So continuing this, we can get an xn in between x naught and xn minus 1 such that gn xn equal to 0, because this process can be considered g triple dash x2 will be 0, g fourth derivative at x3 will be 0, like that it will g fourth derivative at x4 will be 0, like that you'll get a g nth derivative at xn equal to 0, because you can use you'll get a g n minus 1 of xn minus 1 equal to 0 and gn minus 1 of x naught is also equal to 0. So in between x naught and xn minus 1, you can find an xn such that g's nth derivative at xn equal to 0. So you call that xn as c, then what we have is gnc equal to 0. That means fnc minus m into n factorial is equal to 0. So you'll get m equal to fnc divided by n factorial. So this establishes the value of m also. It shows that there exists an m, and that will give you the value of m also. Okay. Now, how does it gives the Taylor series is, suppose that this FNC is a bounded quantity. Suppose that FNC is a bounded quantity. For example, if you assume that Fn is uh, f is differentiable infinitely many times, then each time you will have FNC as a bounded quantity, and this n factorial in the denominator, it is getting bigger, right? So it's just like a constant divided by a very big number which goes to infinity. And x minus x naught, if you consider, it's going to be a fixed number, because your x naught and x will be in a fixed distance. So what happens is, due to the presence of this n factorial, as n becomes 1000, 1 lakh, 10 crore, etc., the right side becomes very, very small and it vanishes. So as n tends to infinity, this term, the last term, will go to 0, and you will get f of x equal to an infinite series. So that's how Taylor series comes. Thank you.